Okay, this is an example of where we have to use two different formulas for power, right? So we've got some power plant here. Okay, and the power plant basically sends out two lines. Okay, and there's a voltage potential between these two lines, a delta V across the line. And it also sends current down the line, right? And so, and there's a transformer inside the power plant, and we say that for the transformer, the current in the primary times the voltage in the primary is equal to the current in the secondary times the voltage across the secondary. Okay? Now, the primary is what goes out, because we're stepping up to a high voltage, low current. So this will be the output. The higher voltage, we always make that the primary. Okay? So that's the power output, but then they talk about power dissipated. Well, the power dissipated, we have these formulas, right, that the power is equal to I delta V, or delta V squared over R, or I squared R. And we typically use this I squared R because this delta V, when we're talking about power dissipated, what happens as the current leaves the power plant, it goes from a high potential here to a low potential over here, see? So there's a delta V that goes along the power line. And that's the delta V that goes into power lost, right? But that delta V is not well defined. The resistance, however, is well defined for the line. That's why we don't confuse ourselves to use I delta V for power loss or delta V squared over R for power loss. We use delta V for power supplied, and that means the delta V across the lines. Okay? I hope that makes some sense. So, to find the power dissipated along the line, we need to find the secondary current squared times the resistance. Now, we already know the resistance is 95 ohms. We just need to find that secondary current. So, or I'm sorry, the primary current, right? It's the primary current here that's going along the line. So the power dissipated along the line is the primary current squared times the resistance. Okay, so plugging into our formula here, we don't know the primary current, but we know the primary voltage is 240,000 volts. Okay, that's what goes out along the line. What's being generated inside the power plant has a secondary current of 140 amps and a voltage of 20,000 volts, right? So this is how much energy goes through the transformer, right? And it's conserved as it goes through the transformer. And that is equal to 2.8 million watts. Well, when we solve this for the primary current, we get 11.7 amps. And so the power lost is 11.7 squared times 95, which is 13,000 watts. Okay, now if we express that as a percentage, the percentage lost is 13,000 divided by 2.8 million. And then we multiply that by 100, and we get 0.46%. Okay, so less than 0.5% is lost. If the power were not sent through the transformer first, then the power lost would simply be the secondary current. That current before it goes into the transformer, which is 140 amps. So we take 140 squared, multiplied by 95, and we get 1.86 times 10 to the 6th watts. Okay, and that percentage loss then is 1.86 over 2.8 times 100, and that's 67%. So a huge amount of power is lost if we don't use the transformer to step it up, and that's why transformers are used. That's why we have high voltage power lines.